So now that we have the initial model developed and we've gone through the verification task to ensure that the model does operate the way we think it does, let's demonstrate how we can use the model to analyze the underlying system, the flexible manufacturing cell. For this experiment, we're going to do two different analyses. First of all, we're going to try to decide how many operators we need in order to maintain stability in the system. And secondly, we're going to try to estimate the system capacity given the current product mix. In order to support our analysis, we're going to define two reference properties to simplify the process. The first reference property we're going to use to specify the initial number of operators, so the population size, and the second reference property we're going to use to specify the mean inter-arrival time. And we'll see why we want to do that in just a second. So let's go to the Definitions ribbon, Definitions tab, Properties, and define our two properties. For the number of operators, it's simply an integer, and we're going to name this num_ops. And for the second property, it's a real property, and we will call this mean IAT. So get to the name and call it mean IAT. And we can give these default values. The mean IAT we'll just make 4.21, which was the inter-arrival time that we used previously. And for number of operators, we will make that value 1. So now that we have our reference properties defined, we can go back to our facility window and specify that our initial number and system will be controlled by the num_ops reference property. And again, you can see the green arrow here indicating that num_ops is a property. Similarly, we will go to the mean inter-arrival time, or the inter-arrival time property, and use the mean IAT property here. So now we have our two newly defined properties. If we right-click on Model in the navigation window and go to the Properties selection, we can now see that we have a Controls section with our two newly defined properties. So number of operators 1, mean IAT of 4.21. And so these are the values that would be used when you run Simio in interactive mode. Also, when we go to the experiment, we now see a new section for those controls, for the number of operators and the mean IAT. And the benefit of using these reference properties is that we can use these controls in the experiment to simplify searching for the values that we're interested in. Also note that I've also defined two additional responses for our experiment. The average WIP, which is simply the num_in_sys average value, and the final WIP, which I used a output statistic to record. So if I go back to the model definitions under elements, you can see that I define an output statistic called final WIP, and the expression for the output statistic is simply the WIP state. Recall that an output statistic is the value of an expression at the end of a replication, and so this in fact does give us the average or final WIP value. And I did this, added these responses just so that we can see those values in the experiment design window without having to check them in the pivot grid. So we can go down in our control section now, and we can have, the values that we had previously. So 1 operator, and let's say 4.21 as the mean inter-arrival time. We can reset, and we can rerun the model. And notice now that the controls are set to the values that we had tested initially. And as we saw when we did the initial experimentation, the average WIP is roughly 1/2 of the final WIP, representing the fact that one operator simply can't keep up with the workload. But what we can do now that we have the experiment defined this way, is define a second scenario, scenario 2, and this scenario will have 2 operators. So now we have 2 operators and a mean inter-arrival time. We'll leave that at 4.21, and let's go ahead and define the third one, scenario 3, where we have 3 operators, and we'll go ahead and do the fourth one also while we're here. Scenario 4, where we have 4 operators. And so by using the numops reference property, it allows us to systematically experiment or define scenarios systematically so that we can evaluate the solution space. Okay, so all 10 of the replications have run for all 4 of our scenarios, and we can see the corresponding results. And so scenario 1 and scenario 4 were the 2 that we tested previously before we updated the model. And now we've added the 2 scenarios where we have 2 operators and 3 operators. And certainly from this initial experimentation, we can see it looks like 2 operators could handle the workload, but we're not quite sure. So we would want to explore that further by increasing the run length or increasing the number of replications for this particular scenario. But from what we can see just from this simple experimentation, 1 operator can't keep up, 3 and 4 can keep up. For our second analysis, we're interested in the system capacity. So if we go back to our facility view, recall that the capacity of a system is defined as the maximum sustainable throughput rate. So it's the maximum rate that we can produce parts, in this case, within our system without the WIP growing without bounds. For our model, the throughput is defined or determined by the in-arrival time. So the shorter the in-arrival time, the more frequently parts will arrive. Okay, so to do the capacity, to identify the capacity, what we have to do is systematically consider different values of the mean in-arrival time. So based on our earlier analysis, let's just assume that we're going to have two operators. And so we can modify our experiment to where we have 2 operators for all 4 cases. And now let's systematically reduce the in-arrival time. So we will keep our baseline case as scenario 1. Then we'll go to 4, to 3, to 2 on the in-arrival time. And so now what we have is 4 different scenarios where we are successively increasing the arrival rate to the system. So when we run our experiment, we can wait and see to reset first, and now run our experiment, and we will wait and see the results. So based on the results of our run, it's pretty clear that the system can't handle a mean in-arrival time of 2. So we've more than doubled the arrival rate from our baseline case, and you can see clearly that the average WIP and the final WIP indicate that the system can't handle this arrival rate. Similarly, when we look at mean in-arrival time of 3, it also appears that the system has some capacity problems here. In this case, again, we have the situation where the mean or average WIP is approximately 1/2 of the final WIP. Not exactly, but approximately. And so that gives us some indication that 3 is going to be a bit difficult. So we can eliminate 2, and somewhere between 3 and 4 is what we'd like to experiment with a little bit more. So how about if we do a 3.75 and 3.5, and let's just run one more scenario. And this time let's have 2 operators and 3.25. So now we've got basically all of the cases between 3.25 and 4 in increments of 0.25. So from these results, it looks like our 3.25 mean in-arrival time is clearly out. 3.5 looks a little bit questionable. 3.75 and 4, as we saw before, looks like we can easily keep up with. So the region of interest now is this region between 3.75 and 4. So let's update this a little bit. Let's put our 3.7 here. We've already got 3.75. Then let's do 3.65 and 3.6. And so now we are pretty comfortable with the 3.75 value, and now so we're exploring values around that. So again, we will click reset and hit run. So here are the results from the latest run, and you can see that 3.6 now looks a bit iffy. It's not really clear what's going on with 3.65. In other words, is it Is it going to be stable in the long run or not? Clearly 3.75 is, as we saw before, and 3.7, again, we're in sort of this unknown region here. So as a result of this test, what I would want to do is do some further exploration of the cases of 3.7, 3.65. And so we can easily do that by unselecting the other scenarios. So we're only interested in 3.65 and 3.7, and now let's increase the number of replications to say 25 for these two cases. So again, go back there, deselect the ones we want. We only want to look at, this scenario and scenario 2 and scenario 4. And now when we run, of course, since we've deselected everything else, only those two scenarios run, so it will run a little bit quicker than before because we're not running all 5 scenarios anymore. So from our extended run of scenarios 2 and 4, when I look again, based on the average and final WIP, it looks like both of these scenarios the system can keep up with. So we're getting more and more WIP as we expect that we would, but we're not ending with twice as much WIP. So again, it's not a certainty that the system could keep up. And we could actually continue this kind of ad hoc analysis by increasing the number of replications or increasing the run length, the replication length, and doing some more exploration around these values of 3.65 to say, for example, if 3.64 would work and 3.63, 3.66, and so on. But we're going to stop here, and in the next video we will look at how we can systematically do the same analysis using OptQuest. So as one final note with this experimentation, if we pick the value mean inter-arrival time of 3.65, we can go back to our static analysis and see what that value relates to in terms of our parts per day that we used as the arrival rate. So I can put my 3.65 here, and 3.65, and then I simply take 1 divided by 3.65, so I invert the inter-arrival time, gives me the arrival rate, and then I multiply by 8 to get an hourly value. And so whereas our initial model, our initial experiment had an arrival rate of 1.9 parts per day, in this case we have 2.12 as our capacity under the given product mix.